So we have one more presentation before the roundtable, and that is by Sirine Fakra from ALS. She's a beamline scientist at ALS's 10.3.2 X-ray microprobe, and she will give us an update and describe future plans for the facility. She's a physicist with a background in geochemistry and geomicrobiology.
So thank you very much for the invitation to this fantastic workshop. So I'm Sirine Fakra. I'm a beamline scientist at the X-ray fluorescence microprobe at the Advanced Light Source, and I'm going to give you an overview of the facility and also some talk about future plans of the tender nanoprobe beamline that will be coming with the ALSU upgrade in a few years from now. So first of all, I would like to go through what the capabilities are, the ALS for X-ray spectral microscopy. And the XFM is part of the diffraction and imaging group, which comprise a set of several beamlines, one for that are primarily doing either tomography or diffraction imaging. There's also a suite of tools for in the soft X-ray range, such as cosmic and STIXOMs and infrared spectral microscopy tools here. And so we have about 40 beamlines at the ALS, spanning from the infrared to the soft X-ray range, to the tender X-ray range, as well going up to the hard X-ray range. So primarily what we have is those sets of techniques, such as micro and nano spectral microscopy, several beamlines, several scanning transmission X-ray microscopes. We have also photon emission microscopy at one beamline. We have a set of cosmic imaging beamline, which does primarily STIXOM, tychography, and tomography. We have also a cryogenic sample prep lab, which is currently being built. And we have as well micro and nano CT at beamline 832 and 1131. And a set of diffraction capabilities, such as for high pressure or for micro diffraction imaging, as well as a tender X-ray beamline that is relatively new at the ALS as well. So at the XFM beamline, we have basically three techniques. We do both at the micron scale. The spot size is roughly 1 micron, and its can range is variable, and it's a trade-off between the spot size and the flux. So we go from 1 micron to 7 micron. We do elemental imaging down to the sodium K-alpha emission line. We do chemical imaging. We do both XANS and XAF, ranging through transition metals. So highlighted in red is on the periodic table is the element that we can reach, where we can do both X-ray fluorescence mapping and spectroscopy. And in black are the elements that are cycle, where we can only do X-ray fluorescence mapping at the moment. So down to sodium K-alpha for X-ray fluorescence mapping. We cannot do spectroscopy on those elements. So basically we are reaching 9 out of 10 of the top elements that are present in the Earth's crust. The only one we are missing is oxygen. Those techniques, both actually XAS and X-ray diffraction, strongly rely on databases and computational modeling, and that's currently the bottleneck. There's strong effort to actually unify these databases, and I strongly hope they continue. The latest development we have at the XFM is in collaboration with David Shu's group, where we built basically a tender X-ray chamber for actinide and rare earth element science. And we are, so this is basically a picture of the chamber. We are looking at, we developed this basically to improve the sensitivity of the detection at phosphorus and sulfur, and as well as being able of imaging elements that are below 1000 eV. We have X-ray fluorescence, and we are implementing transmission mode as well. And right now we are able in about 3-minute acquisition to detect fluorine on standards. And so that's one example that I'm showing on Teflon here. And these pics are coming from a Kapton tape that where Teflon was where the Teflon was mounted on. As several speakers have already mentioned, uranium fibers are especially appealing with the X-ray microscope technique, because the beam size is roughly about the same as the penetration depth at this energy. And we saw basically a clear energy shift between uranium-4 and uranium-6. We are currently developing and conceiving a tender X-ray chamber for cryogenic sample as well, and studying the potential for including high resolution XANEs in the future. So the main popular tool at the beamline, and this is for one of the most popular elements, really is that we started back several years ago with Matthew Marcus and myself, was to look at classifying data, classifying XANEs data according to valence state. And doing that was especially relevant at the time, and is still relevant actually, because we don't have a lot of standards that are relevant to interpret this data. There's more than 1,000 minerals, and obviously we don't have in any database right now all these minerals recorded. So there's a need to be able to classify these data very rapidly, and we're able to do this by looking at the normalized absorption values, two specific energies here that I'm showing on these absorption spectra for several minerals that are commonly found, and look at this normalized absorption value as two specific empirical energy, and we are able to classify the one plotted versus the other, allows us to clearly distinguish and cluster several the data according to oxidation states. So these are each standard is each spectrum is basically reduced to a data point on this graph. And as you can see, we can clearly distinguish between metals and sulfide and iron 2 and iron 3. I've developed this method further for metalloids such as selenium, and further for manganese and arsenic. And there is so that has been extremely useful for any unknown spectra. Combined with least square linear combination fitting, this has revealed to be a pretty powerful tool, as well as combining with micro-XRF spectra altogether. We have various sample environment. This is the traditional configuration at the beamline, where we look at basically the sample in air, and we have a new X-ray diffraction camera. We have two sets of detector, and one for higher energy and one for low energy for anything below 3 keV. The main ingredient of the beamline is a cryo stage, which basically allows for sample cryo transfer, and which is also TEM compatible. You can mount a TEM cartridge on it, and it allows XRD. We have also a Peltier stage to look at samples that are larger, and obviously that one is not reaching liquid nitrogen temperature. And because I have very short amount of time, I will just go through one recent work that is ongoing that is very exciting from a collaborator of mine, Tanja Bozak, with Jian Gong. And where we are basically looking at the formation of nodules on Mars. So here I'm showing the Gale crater, and what we so those are images from the rover mission. There's several missions, so one of them, and where you see concretion on the surface, and we basically are trying to Tanja's group is trying to identify how how the formation of clays occurs on Mars and what's the formation process. So that's something that that we've looked into. And so for this, we took some Tanja's group took some basal glass from the Capitán volcano in New Mexico that has very similar composition than the basalt glass found in Mars. And did this experiment where basically the basalt glass was weathered for several months in water and a composition of CO2 and nitrogen that mimic ancient Mars condition. And what was found is that hydrogen gas was produced, and some concretion were formed, and some basically nodules were formed at the surface. It's very similar to the nodules found on Mars. And doing diffraction after several months of weathering, augite was found, and so was the primary phases form, and as well as other pyroxene and olivine. Augite was the primary pyroxene form, and looking under SEM and optical microscopy, we found these grains with a coating here that you can see in dark here from these basalt grains. And what was found is that there's a kind of a cementation process occurring, and that's what we image at the microprobe beamline. So it's one of these area and magnesium-rich area that is sitting on the edge of these grains. And what we confirm is the presence of augite, and we also found magnetite. So altogether, these results pointing to basically the formation of the water being basically converted to hydrogen gas, and iron was being oxidized to magnetite. And that process basically would be one possible route for the formation of clays on Mars. So that's ongoing work where we are trying to characterize more this magnetite particle, which John has found to be nanometer size through other technique, which I won't go into. Now I'm going to go into the LSU upgrade, and which we are right now during CD2 and approaching the CD3 phase. What the basically in short, what the LSU upgrade will mean will be a source that will be much more reduced horizontally, and with about 100 times higher brightness for undulator beamlines, higher flux. And there will be this future tender beamline, which will replace the X-ray fluorescence microprobe beamline, which will have much more higher flux. There will be basically two branches. One will be a scattering branch, the other one will be a nanoprobe a branch. And on a nanoprobe branch will be basically a silicon 111 monochromator, a pair of KB mirrors, such as what's existing on the X-ray fluorescence microprobe. But in addition of that, there will be a zone plate that will be used to focus this virtual source here onto the sample that will now be oriented at 90 degrees instead of 45. And there will be fluorescence yield and transmission yield, as well as X-ray diffraction. So the energy range will be between 2 and 8 kV, so reduced. That's on the bad side. The good side I will show you on the next slide. The resolution will be much improved at 100 nanometer. And there will be this pair of KB mirrors plus zone plate, which would provide fluorescence for fluorescence 100 nanometer with typography at the 10 nanometer level, as well as tomography. The the elements that we will still be able to access are fundamentally still majorly important for the geoscience community, because we'll still be able to access phosphorus, sulfur, potassium, calcium, and iron. The several areas, so the program will be transferred. The user program will be transferred, and we will still be able to tackle nicely all these areas. And there will be basically 2 end stations. One of them is already existing, end station 1 and end station 2. This one will be more deep magnified, so a smaller spot size, though that will depend on which zone plate we will actually use. That is not set up yet. This end station 2, this is basically this is an end station that is already existing at DLS that will be basically moved. It includes tomography, typography, spectral microscopy. It's equipped with a commercial cryo TEM holder. You can basically, so the sample is sitting here. You can basically rotate this as you would do on a cryo TEM. It's basically using the exact same technology that was developed by the TEM community for many years, for many decades. It's compact and rigid for high stability. And the upgrade that we will have is, of course, adding a fluorescence detector, some custom sample holders, and a high energy pixel detector as well. So the main feature areas, and I'm citing a few that we're really targeting with this end station will be, for instance, on looking at the reconstruction of surface layer on bacteria by imaging in 3D and correlating this soft X-ray data on the new tender beamline. Sorry about that. To the EM data, and this will be used. This set of data combined with metagenomic data will allow us to basically understand how the microbial community at large function in terms of, and that has an implication in biogeochemical cycling, and especially sulfur, phosphorus. We'll be able to look at the mineral mineral cell relationship and how the minerals nucleate inside or outside cells through imaging, and combine that with the metagenomic data set. Sorry about this. Another set of will be on the functional material and self-assembly. And here's a picture of a coprolite, and we'll be able to nicely resolve these features and the distribution of trace metals as well. And here's another example from the X-ray fluorescence microprobe, actually from a couple of years ago, on sponges that accumulated bacteria, that host bacteria, and only one of them was responsible for a huge accumulation of arsenic and barium. They, as you know, sponges take up trace metals, and these bacteria, there was only one bacterium responsible for the accumulation of arsenic and barium for the sponges, and they managed to isolate it. This was work by Ray Karen and Mifra Allen from Tel Aviv, Israel, and we through the microprobe we found that arsenic, and I'm showing here the spectra at the time. So these were all data collected at 95 Kelvin. And as you can see here, there's a chemical shift, as previous speakers I've shown, between arsenic 3 and arsenic 5. And we were able to, by least square linear combination fitting on some specific areas on these filamentous bacteria, to identify pharmacolite as one of the main compound found, which is basically a hydrated form of calcium arsenate. And we concluded from there that these bacteria convert soluble arsenic 5 into a solid form of arsenic 5. And they also further did some cross-sectioning of these filamentous bacteria to find the location of where this arsenic mineralized form was stored, and it was stored in compartment and vesicular compartment in these bacteria. So this was all very, very exciting at the time. And then I will conclude by this project that is ongoing, which is in an energy range that would be nicely accessible by the future Thunder nanoprobe, where basically we are looking at, as you may or may not know, I jumped it a bit too fast here. As you all know, I would imagine, lanthanide are very much ubiquitous across the surface of the Earth, and they have been so far pretty much understudied because of their small size and their dispersed distribution in soils. And we started this project where we basically, and they have been assumed to be not taken up by, not much by any form of life. However, they are quite biologically active, and so what we and they can be used as a cofactor in numerous enzymes. And what the work we started was to look at the rare earth distribution in soils from the East River Critical Zone Observatory, and this is work done in collaboration with Jill Benfield Group. And we are basically so far finding an approximate ratio of serum and lanthanide about 2:1. We found that the lanthanide are sparsely concentrated, and we are developing further work to try to understand the ability of the lanthanide for the microorganisms that are present at this site in coordination with metagenomic data. And that's primarily work from Jacob Roberts in the Jill Benfield Group at UC Berkeley. So to conclude, I would like to acknowledge the numerous people at the Advanced Light Source that have contributed to the techniques that I've introduced here, and Dula Parkinson, David Shapiro, for Cosmic, Martin Kuntz, Harold Bernard, Matthew Marcus, Alistair McDowell, Rich Lastry, Bruce Rood, Andrea Teller, which is the cheerleader of our ALS, and I would like to thank the ALSU team led by our partner and Elaine Dimasi. Thank you very much again.
Okay, thank you. We're actually quite a bit late on time here. So Sirine, there's a couple of questions. No worries. There's a couple of questions in the chat. Maybe you could answer, you could respond to those in the chat.